1. Brief history of virtualization. If you are like me, when I was a young technologist, I assumed virtualization was a brand new technology. If you are like me, then you would be surprised to learn that virtualization, as a concept, has been around since the inception of modern computing. The emergence of the technology started in the 1960s, when International Business Machines, IBM, was the market and industry leader in computational technologies and introduced the concept of running multiple virtual instances of an operating system on a single physical machine. IBM continued to develop the technology into the 1970s and incorporated running multiple virtualized instances concurrently in their mainframe computing space. Starting in the 1990s, VMware was founded and developed virtualized solutions for desktop computers using the x86 architecture, which allowed users to run virtualized instances on their home computers. With the streamlined use of virtualization in home computers in the 2000s, data centers and enterprise users began to incorporate virtualization into their large-scale networks with added ease because more tools and competition entered the market. Fast forward to the 2020s, and virtualization is a standard across all network domains. 1. Virtualization. Virtualization in most use cases in computer networking refers to the creation of virtual instances that represent physical network infrastructure. One of the primary themes of virtualization comes down to efficiency and improved resource allocation. Virtualization can apply to specific use cases like network virtualization, server virtualization, storage virtualization, desktop virtualization, and application virtualization. Network virtualization involves partitioning a single physical network into multiple virtual networks. Each virtual network operates as if it were an independent network. Network virtualization enables the creation of isolated network segments for resource allocation or security reasons. Server virtualization involves running multiple virtual instances of servers or operating systems on a single physical server. This allows for better resource utilization and simplifies server management tasks such as provisioning, routine maintenance, and disaster recovery. Worst-case scenario. Storage virtualization abstracts physical storage resources into virtual storage pools. These storage pools can be dynamically allocated to meet the current demand of the user or network. This technology offers features like data migration, redundancy, and scalability without disrupting service availability. Desktop virtualization enables users to access their desktop environment remotely using virtual desktop infrastructure, VDI solutions. This technology allows centralized management of the proprietary desktop environment, enhances security, and enables support for a diverse range of devices. Application virtualization separates applications from the underlying operating system, allowing them to run in isolated environments known as containers. This facilitates easier deployment, management, and scalability of applications across different computing environments. 1. Hypervisor. A hypervisor is not a virtual machine, but it contains the software and the firmware needed to create and execute virtual machines. Hypervisors come in two flavors: Type 1 hypervisors, bare metal hypervisor, and Type 2 hypervisor, hosted hypervisor. A Type 1 hypervisor runs directly on the underlying computer's physical hardware and interacts directly with all of the CPU resources, memory, and storage. The Type 1 hypervisor takes the place of the operating system and are referred to as bare metal hypervisors. In theory, this increases their security because there is nothing in between the VM and the CPU, reducing its footprint for attack vectors. Type 1 hypervisors are primarily used in production or corporate settings with the real-world purpose. Examples of Type 1 hypervisors include VMware ESC, Microsoft Hyper-V, and KVM, kernel-based virtual machine. Figure 1. Type 1 hypervisor, bare metal. A Type 2 hypervisor runs as an application on top of the host operating system. Type 2 hypervisors are typically used in a home setting or individual use. Popular reasons include small-scale testing, analyzing software applications in a controlled environment, sandboxing, or tinkering with the software for personal use. Examples of Type 2 hypervisors include applications or technologies like VMware Workstation, Oracle VirtualBox, and Parallels Desktop. Figure 2. Type 2 hypervisor, hosted hypervisor. 1. Virtual machine formats. Virtual machine formats are specific file formats used to store and encapsulate virtual machines and their associated configurations, operating systems, applications, and data. These formats enable VMs to be easily moved, deployed, and managed across different virtualization platforms like Virtual Machine Disk, VMDK, Virtual Hard Disks, VHD, Open Virtualization Format, OVF, and Amazon Machine Image, AMI. Virtual Machine Disk, VMDK, was developed by VMware and is a widely used virtual disk format for VMware applications like VMware SC, VMware Workstation, and VMware Fusion. VMDK files store the contents of the virtual machine's hard disk drive, including the operating system, applications, and data. Virtual Hard Disk, VHD, is a virtual disk format developed by Microsoft for its Hyper-V virtualization platform. It is also natively supported by other virtualization platforms like Oracle VirtualBox and Quick Emulator, QEMU. VHD files contain the disk image of a virtual machine and can store several types of data. Open Virtualization Format, OVF, is a platform-independent open standard for packaging and distributing virtual appliances for VMs. OVF packages typically consist of multiple files, including a descriptor file, OVF file, describing the virtual machine's metadata, and one or more disk image files. Amazon Machine Image, AMI, is a proprietary virtual machine format used by Amazon Web Services, AWS, for creating and deploying virtual machine instances in the cloud. AMIs contain the operating system, applications, and other data required to run a virtual machine on AWS EC2 instances. 1. Origins of Amazon Cloud AWS. Amazon Cloud AWS was developed in the early 2000s to meet Amazon's increasing need for information technology and needed more control over how it is scaled. Andy Jassy is the person accredited to spearheading the development of AWS. Around 2006, Amazon launched its first commercial offering with Amazon S3, Simple Storage Service, with its intended audience being developed. Since then, Amazon has experienced tremendous growth and claimed a large share of the market when its AWS services provided a robust cloud computing solution. AWS provides the backbone for agile methods like ones deployed at Netflix and has diversified its portfolio by providing corporate solutions to federal contractors like Science Applications, International Corporation, SAIC, who extend those services to NASA and the US Navy. AWS has proved to be a successful capital venture, and it currently accounts for 12% of all of Amazon's revenues. 1. Toward a unified ontology of cloud computing. Ontology is defined as a set of concepts and categories in a subject area or domain that shows their properties and the relations between them. The ontology of cloud computing can be looked at as a stack divided into 5 layers: applications, software environments, software infrastructure, software kernel, and hardware. Figure 3. 5 layers of cloud ontology. Cloud application layer is the layer that most users will interact with. The application layers host the web-based portal with the login. Having an active application that is managed by a third party relieves the host company of the responsibility of maintaining its code. Having a web-based portal also removes the restrictions of hardware requirements and relieves the end users of any CPU-based processes that may come with rendering an application. Cloud software environment is intended to be used by cloud applications developers to implement their code and deploy their resources on the cloud. The cloud providers supply the developers with a programming language-level environment with a defined set of APIs to standardize the interaction between the work environment and the cloud application. This layer is also referred to as Platform as a Service, PaaS. The cloud software infrastructure layer provides fundamental resources to other high-level layers, which in turn can be used to facilitate the construction or creation of new cloud applications. The 3 services that define this layer are computational resources, where VMs are housed, data storage, how data in VMs are accessed, managed, and communication protocols, the method in which users are able to access VMs and their resources. The software kernel provides the basic software management for the physical servers that compose the cloud. The kernel is intended to make the shared allocation of resources as efficient as possible. The firmware-hardware layer is the physical component of cloud ontology. This layer is also known as the backbone of the cloud. The primary users in the layer are the actual cloud providers and will rarely be seen by the end users or the customers. This layer is referred to as a hardware as a service, HaaS. 1. Containers. In containerization, a container refers to a lightweight, standalone executable package that contains everything needed to run a piece of software, including the code, runtime executables, libraries, and dependencies. Containers are isolated from each other and from the underlying infrastructure, allowing applications to be easily scaled and deployed across different environments. The Open Container Initiative, OCI, defines standards for container formats and runtime specifications. Within the OCI, a container is typically described as a standardized, lightweight, and portable executable format that encapsulates software and its dependencies, making it easy to build, share, and run containerized applications across different platforms and environments. Linux Containers, LXC/LXD, is a lightweight virtualization technology that allows you to run multiple isolated Linux systems, containers, on a single host. In the context of LXC/LXD, a container is an isolated environment that shares the host operating system's kernel, but has its own file system, processes, and network stack. Containers in LXC/LXD are often used for resource isolation. Docker is a popular platform for containerization that allows developers to package and distribute applications as containers. Docker creates the container as an instance of a Docker image. The Docker image, like containerization, is a lightweight, standalone, executable package that contains everything needed to run an application. Docker containers are portable, scalable, and can be easily deployed and managed using Docker's tools and APIs. Snapcraft is a platform for building and distributing snaps, not to be confused for Snapchat. The snaps are a type of containerized software package used primarily on Linux systems. Snaps run a specific Linux-friendly version of containerization, in which the solutions are standalone applications with its own portable code, runtime, libraries, and dependencies, allowing them to be moved around and used in a Linux environment. In a broad sense, containers can refer to any technology or platform that provides containerization capabilities, like Docker or Linux LXC/LXD. This may include container orchestration platforms like Kubernetes, container runtimes like Containerd, or other containerization solutions that follow similar principles of encapsulation, isolation, and portability. 1. Orchestration. A virtualization orchestrator refers to the automated coordination and management of virtualized resources, including virtual machines, VMs, containers, networking, and storage across distributed environments. Orchestration involves the automation of tasks such as provisioning, deployment, scaling, monitoring, and lifecycle management to ensure the efficient operation of virtualized infrastructure and applications. Kubernetes is an open-source container orchestration platform for automating the deployment, scaling, and management of containerized applications. Kubernetes schedules containers onto nodes, also known as pods, managing their life cycles and ensuring the desired state of the application across clusters of servers. Kubernetes provides features such as service discovery to deploy and operate applications reliably at scale. Charmed Kubernetes is a distribution of Kubernetes that is packaged, evaluated, and maintained by Canonical. Canonical was developed by Ubuntu. Orchestration in Charmed Kubernetes involves using Juju charms to deploy and manage Kubernetes clusters across different cloud and on-premises environments. Charmed Kubernetes simplifies the installation and configuration of Kubernetes, as well as the integration with other services and tools through the use of Juju. Mirco K8s, pronounced Micro K8s, also known as Micro Kubernetes, is a lightweight Kubernetes distribution designed for development, testing, and edge computing environments. Orchestration in Micro K8s involves automating the deployment and management of containerized application on single-node Kubernetes clusters. Micro K8s provides a streamlined Kubernetes footprint, making it easy to set up and run Kubernetes-based applications locally or in resource-constrained environments. OpenShift is a container application platform built on top of Kubernetes. Orchestration in OpenShift involves automating the deployment, scaling, and management of containerized applications across clusters of servers. OpenShift provides additional features beyond Kubernetes, such as integrated developer tools, enhanced security features, and built-in monitoring and logging capabilities to streamline the application development and deployment process. Juju is a service modeling and orchestration tool that simplifies the deployment and management of complex applications on various cloud and container platforms. Orchestration in Juju consists of defining the desired state of the application and its associated components using Juju charms. Juju then automates the provisioning, configuration, and integration of these components across different environments, allowing for rapid and consistent application deployment. And private cloud. A private cloud refers to a cloud computing environment that is dedicated to a single organization or entity, typically within their own data center or hosted by a third-party provider. Unlike public clouds, which are shared by multiple organizations and accessible over the internet, a private cloud is exclusively used by a single organization and may be hosted on-premises or in a managed hosting environment. OpenStack is an open-source computing platform that provides a set of software tools for building and managing both public and private clouds. Organizations can deploy OpenStack within their own data centers to host their own private cloud services. OpenStack is used to provide and manage virtualized resources, such as configuring storage volumes and networking components within their own infrastructure. OpenStack enables organizations to create scalable, elastic, and universally available cloud environments that provide on-demand access to computing resources for the internal users and applications.